All right, let's talk about the D block elements. These are the metals that have, quite literally, built our modern world. I mean, from the iron in our skyscrapers to the gold in our technology, they are everywhere. Okay, so let's just jump right in with a puzzle. Take a look at these solutions. Just, wow. How do they get these incredible, vibrant colors? What is going on at the atomic level that makes one blue, another one pink, and a third yellow? Well, the answer, as we're about to find out, is hiding deep inside the atom. So to figure that out, we first need to know where to find these elements on the map, right? The periodic table. They live right here, smack in the middle. This big block is called, you guessed it, the D block. It's like a massive bridge connecting the super reactive metals on the left with all the nonmetals over on the right. And we're not talking about some obscure elements you only see in a lab. Nope. These are the heavy hitters, the household names. You've got iron, the foundation of all modern construction, copper, the thing that literally powers our electronics, and, of course, the ones we've treasured for centuries, silver, gold, and platinum. So what's their secret? What's the one thing that defines them and gives them all these cool properties? It all comes down to one fundamental thing, their electronic structure. Specifically, the way their electrons hang out in these things called d orbitals. Okay, so if you look up the official scientific definition, it gets right to the heart of it. A transition metal is any metal that has a d subshell that isn't completely full. It's this incomplete status, this kind of in-between state that is the key to everything. It gives them this amazing chemical flexibility. And this comparison right here shows you exactly what that means. Let's look at the very first element in the row, scandium. It's got just one lonely electron in its d orbital. So, yep, it's a transition element. But then you go all the way to the other side to zinc. Its d orbital is totally full, 10 out of 10 electrons. So by that strict definition, zinc doesn't actually count as a transition element. Kind of weird, right? Now, here's a little rule of thumb in chemistry that you absolutely have to know. Atoms are always looking for stability. It's like their ultimate goal. And it turns out there's a special kind of stability when their electron orbitals are either exactly half full or completely full. This one idea causes some really wild exceptions to the normal rules. And boom, here's that principle in action. Check out chromium and copper. If you just followed the basic rules, you'd expect a different electron configuration. But look what they do. They actually take an electron from their outer s orbital and bump it up to the d orbital. Why would they do that? To hit that stability jackpot. For chromium, it gets a perfectly half-filled d orbital, and for copper, a completely full one. It's a trade-off that's totally worth it for the atom. All right, so that's the tiny atomic level secret. But how does that translate to the real world? How does this weird electron behavior explain why these metals are so incredibly strong and hard? Let's connect the dots. You know, their famous strength and super high melting points? It's all about how tightly their atoms are bonded together. And here's the deal. It's not just their outer electrons holding hands. Those inner d electrons get in on the action too. The more of these unpaired d electrons you have, the more bonds you can form, and the stronger the whole thing is. We can actually measure this with something called enthalpy of atomization. It's basically the energy you need to just rip the atoms apart from each other. And just look at the difference. Tungsten, with lots of unpaired electrons, has a massive value. Compare that to zinc, which has 0 unpaired d electrons. It's way, way weaker. All right, now let's talk about size. This is where things get, well, a little weird. As you go down the periodic table, atoms are supposed to get bigger. It just makes sense, right? You're adding more shells of electrons. And that's true when you go from the first row of d block elements to the second. But then something strange happens. The atoms in the third row are almost the exact same size as the ones right above them in the second row. I mean, they're practically identical. This breaks the pattern completely. So what in the world is going on here? Why don't they get bigger? The answer has this really cool name, the lanthanoid contraction. So here's the story. Before you start filling in that third row of d block elements, you first have to fill a whole new block of orbitals called the f orbitals. Now, these f electrons are, well, they're terrible at their job. Their job is to shield the outer electrons from the massive positive charge of the nucleus. Since they're so bad at it, that powerful nucleus can reach out and pull all the other electrons in much tighter. This pull effectively shrinks the atom, canceling out the size increase you'd normally expect. Okay, so let's get to the really famous stuff, their chemical properties. And by now, I bet you can guess the reason. Yep, once again, it all comes back to those amazing, partially filled d orbitals.
They are the reason these metals can have so many different charges, why they're magnetic, and, of course, why they have those brilliant colors. You see, the energy difference between their outer s electrons and those d electrons is super small. That means they can pick and choose how many electrons to use when they make bonds. This gives them an absolutely insane range of possible charges, or what we call oxidation states. And you can see it peaks right in the middle. Look at manganese. It can have a charge of anything from +2 all the way up to a mind-boggling +7.
Okay, for the next two big ideas, magnetism and color, it all boils down to one simple thing: electrons that are sitting all by themselves in an orbital. We call these unpaired electrons.
So every one of these lonely, unpaired electrons is spinning, right? And that spin creates its own little magnetic field. When you have a bunch of them, like in a manganese ion, their tiny fields add up, and the whole ion becomes attracted to an external magnet. That's a property called paramagnetism. The more unpaired electrons, the stronger the attraction. But if you have 0 unpaired electrons, like in a zinc ion, something else happens. The material is actually weakly repelled by a magnet. We call that diamagnetism. And here's the amazing part. This brings us right back to where we started, to those beautiful colors. Those exact same unpaired electrons are the reason for the whole show. We finally solved the mystery from the beginning.
Okay, so think about it like this. White light from a lamp is basically a mix of all the colors of the rainbow. When that light shines through one of these solutions, an unpaired electron can absorb a very specific color, a specific amount of energy, and use it to jump to a higher energy level. Our eyes then see all the colors that weren't absorbed, the colors that are left over. So if the solution absorbs yellow light, it's going to look blue to us. And here's the final piece. If there are no unpaired electrons, like in our good friend the zinc ion, then no light gets absorbed. The light just passes right through, and the solution is completely colorless.
So let's wrap this up by looking at how all this cool chemistry plays out in the real world. One of the most important jobs for transition metals is as industrial catalysts. You know how they can flip-flop between different charges so easily? Well, that makes them amazing catalysts. They can speed up a reaction by offering it an easier path to follow. In this case, the iron ion acts like a chemical matchmaker. It goes from a +3 charge down to a +2 and then right back up to +3. At the end of the day, the iron is completely unchanged and ready to do it all over again. And it's not just about speeding things up. These elements are also used as powerful players in reactions. Let's look at a really important compound, potassium dichromate. This stuff is a potent oxidizing agent, meaning it's really good at snatching electrons from other chemicals. You'll find it used in all sorts of industries. And this is where it gets really neat. When you dissolve this stuff in water, it exists in this delicate dance, an equilibrium, that you can totally control just by tweaking the pH. If you make the solution basic, you get this yellow ion called chromate. But if you add some acid, the whole thing shifts, and it transforms into this vibrant orange ion called dichromate. It's a fantastic, colorful example of a chemical equilibrium at work. So when you think about it, from the incredible strength of a steel beam, to the flash of color in a test tube, to the catalytic converter in your car, so much of it traces back to that one simple, elegant feature, those partially filled d orbitals. It really makes you look at the world a little differently, doesn't it? And it makes you wonder, what other amazing secrets are these elements hiding in plain sight?